Okay, now we consider a very similar situation. We got a charge Q on a capacitor, and we know the capacitance C. We want to find the work contribution, the work required to transfer a small charge, delta Q. Well, our reasoning is the same as it was when we had the numbers. The capacitance is charge over voltage, so the voltage is charge divided by capacitance. Just the same type of calculation we did here when we divided the charge by the capacitance. Could be reasoned out by units, but the idea is the same in any case. So from the charge and the capacitance, the point is we can determine the voltage. Having determined the voltage, we then multiply that voltage by the amount of charge transferred to see how much energy is required to transfer it, or how much energy is associated with the transfer. And we get the voltage being Q over C, multiply that by our delta Q. So we have Q, which is the charge on the capacitor, divided by the capacitance, C, multiplied by the charge transferred, the additional charge that's transferred when we already have the charge Q on the capacitor. So that's our delta W. Now the question of how we charge this capacitor up from zero charge to a full charge, Q sub F. Well, you think of what happens. You throw the switch, the voltage starts, the voltage creates an electric field that starts pulling electrons off here and depositing them here. Actually, it starts pulling electrons off of here and depositing them here. I think in class I was going the wrong way with that. You get the idea though. Because if you pull electrons off of here and deposit them here, this ends up positive, this ends up negative. That's obvious. So obviously I'm not having the greatest day here, but it's not bad. Okay, at least not by my standards. Okay, so we pull an electron off of here, and it pretty much gets around here for free, because there's no resistance through here. We assume we have a zero resistance source, although no such thing really exists. But the first electron gets around essentially for free. The next electron has to come over here, and it's being repelled by the field created by the electron that's already on the plate. So it's got to do a little work. And then the next electron has to fight the field due to two electrons over here, and so forth. So as charge gets transferred, it takes more and more energy. And of course, that's inherent in this expression, because this is the amount of charge that's already been transferred. First one electron, then two, then three, or one unit of charge, then another, small units of charge, and that's multiplied by the charge you're transferring as this accumulates. Well, what do we get then? Well, we get a delta W for every one of these delta Q's, starting from charge 0. We have 0 coulombs times our first delta Q, which gives us 0 work. But then the next one, we have a little charge. We multiply that by delta Q. Well, to go from uncharged to charge QF, full charge or final charge, we have to add up all our delta W's. So we add up all our delta W's. That means we got to add up all the expressions of the form Q over C times delta Q, which means that in the limit, we're going to be integrating Q over C dQ from charge 0 to charge QF. Now, you want to work out the Riemann sums in some detail so you really understand how this integral comes about, but that's a synopsis of how it's done. This is an easy integral to do. Factor out the 1 over C, and you just end up with the integral of Q dQ. The antiderivative of Q with respect to Q is Q squared over 2. Evaluating that between 0 and QF, we end up with QF squared over 2. So we have QF squared over 2 times the 1 over C, so you get the C down here. So this is the work required to charge up the capacitor. Now, I'm going to write a couple of things down here and then come back. No, I'm not. That's going to go in the next video. So we're going to stop with that idea.